So, hey, I want to say something before we begin, because we're living in crazy times. I know this is an international conference, so many of you are not based in the U.S., but I just think we need to recognize something that's going on, which is that on Friday, the National Institutes of Health budget was ordered to be slashed tremendously, with all indirect costs going down to 15%. NSF is facing really, essentially, existential threats to funding cuts. This is all subject currently to litigation. There's several temporary restraining orders that have been put in place by judges, but those, as of this morning, reporting says they're being ignored. So the funding is still being cut off. But secondary from those temporary restraining orders, we're seeing programs that should be actively soliciting proposals this year being removed. So for example, the Racial Equity in STEM Education program from NSF and the MPS Ascending Postdoctoral Research Fellowships, these have been archived. So these are supposed to be getting proposals this coming year. They're gone, right? And that is not subject to things like judicial orders. That's just happening without a lot of pushback. And there's a lot of history for math and science institutions, both like universities, but also professional societies, in moments like this, kind of stepping back and focusing on protecting the science. And I think it's important when we're at critical moments like this to be very clear with what our values are. And so I just want to make a public statement about my values. You're welcome to disagree with them, because I think it's important that we be real clear about what we want. And so I believe that our collective goal should not be the advancement of mathematics. And when we're fighting back against cuts to NSF and NIH, things like that, I'm not talking about math. Our goal should be the advancement of our own humanity. Mathematics is a human endeavor. It is people that do mathematics, right? And so the first and foremost priority when we're talking about moments like what we're in is not about what's going to happen to math. It's about what's going to happen to the people doing math. And I think this is an opportunity for us to double down on the fact that our mathematical communities can, and I feel should, be centered on care and compassion above all else if we choose that. And I think if anybody who's wanting to advance mathematics and cares less about the people, if we care about the people, the math will follow. And I think that's just a really important thing to just remember in times of crisis when everybody wants to lose their heads and is worried about all the money stuff, okay? Anyway, so I just wanted to start with a comment about that. All right.
We emigrate.
So, yeah. No, we got to figure this out. So anyway, I know this impacts some people more than others, but especially, it's a big deal. I think it's going to impact everybody everywhere. So, all right, so on to the math. That's why we're here. So there's a lot of grad students here. There's a lot of grad students here who do not work in my area. And there's also a lot of people here who do work in my area but might not know what, everything about what I'm talking about. So part one of the talk is going to be a survey talk about geometric and algebraic properties of lattice polytopes. I'm going to kind of focus on symmetric edge polytopes because I want to really try to focus on bringing everybody in. Hopefully, even if you're an expert, I'll say a few things that might be new for you. And in part two of the talk, I want to talk about work by me, Katie Bruegge, and Matt Kahle about facet counting. Okay. So, part one. So a lattice polytope is the convex hull of n lattice points, which just means a vector with integer coordinates in m-dimensional space. You can also describe it as a bounded intersection of a finite set of closed half spaces. You got to be a little careful here. If you take this bounded intersection as your starting point, you got to check and make sure the vertices are integer points or lattice points. So it's always easier to know you have a lattice polytope if you start with integer vectors and take the convex hull, and the problem is the facets. If you go the other way, you got a lot more to check, so to speak. And D is always going to denote the dimension of P for this talk. So this is a lattice zonotope. I think Andres made this picture for a survey article we wrote. And then this is a picture of a lattice triangle. As you can see, the vertices are at 0, 1, 1, 0, and -2, -3. So every vertex is an integer point. Yeah.
Is it possible for D to be less than M in this case?
Absolutely, yes. And in the symmetric edge polytopes, that'll be the case. Yep. Okay. Another thing that I want to emphasize is that we typically replace Euclidean volume with the normalized volume. So you hear lots of talk about volume among people in this field. And if you're not used to it, what you do is you take the Euclidean volume, little v, and you multiply it by dimension factorial. And that gives you this normalized volume, capital V. And every time for the rest of this talk, if I say volume, I mean normalized volume. And you might ask, why do you do that? Well, one reason, there's a lot of reasons, but one of the reasons is that this normalized volume is always a positive integer. And so if you're a combinatorialist or an algebraist, positive integers are just better. Anyway, so they're better than fractions, so that's what we're going to do. All right.
Separately for each facet dimension? Right, face dimension?
Yeah. So if you're not full dimensional, then what this Euclidean volume means is it's Euclidean volume relative to the lattice sitting inside that application.
But I mean for a face of lower dimension on the polytope, do you renormalize with different d for that face?
Yeah.
Okay.
Yep. Exactly. All right. So I told you what a lattice polytope is. What's a symmetric edge polytope? So you start with a finite simple graph G. Then the symmetric edge polytope, which is, I'll abbreviate SEP, I might say both, is the convex hull of a pair of vertices for each edge. So you take each edge in the graph, and you take EI minus EJ. As usual, EI is the standard basis vector. It's a 1 in the ith spot, 0s everywhere else. But you take EI minus EJ, and you take EJ minus EI. So there's this centrally symmetric in Euclidean space pair of points, hence the symmetric edge polytope, okay? So pair of points for each edge. This is the vertex description, because I'm telling you the convex hull, the facet description, which are the maximal non-trivial faces. Those will show up later in the talk, okay? So here's an example. If I take K3 with vertices U, V, and W, then you have this nice hexagon, which you get with these 3 pairs of antipodal lattice points. And this is where what you'll notice right away is, since these are all roots of type A, right? Every one of these vertices is orthogonal to the all ones vector. So these polytopes sit in the perpendicular space, the orthogonal space to the all ones vector. So they're never going to be full dimensional in R to the V, right? Okay, and that image is Katie Bruegge's PhD thesis. So I want to acknowledge that. I did not make a picture that nice. That was all her. Okay. All right. So what do we do with a lattice polytope? Well, one of the things that we do is we count the lattice points in integer dilates of the polytope. There are reasons you might. Oh, did you have a question? No. There's reasons you might want to do this for number theoretical purposes or for algebraic purposes like Hilbert series stuff, or combinatorial purposes like counting magic squares. There's a lot of different reasons you would want to do this. So what we do, if you look in this lower right corner, is you can start with an integer polytope. This is just a polygon, a 5-gon. Every vertex is a lattice point. You dilate it by a factor of 2, then a factor of 3, then a factor of 4. For every dilate, you count the number of integer points inside, and that includes the boundary. So interior and boundary, count all the lattice points, okay? That is what this function is. T times P intersect Z to the D. You count. That gives you an infinite sequence of integer point counts. Make those the coefficients of your power series. That's called the Ehrhart series. And this lovely theorem due to Ehrhart is that this collapses as a rational function. The denominator is 1 minus Z to the dimension plus 1. And the numerator is this polynomial of degree at most the dimension. Okay? This is just a general fact about polynomials. So it turns out that this integer point counting function, TP intersects Z to the D, that's actually a polynomial of degree equal to the dimension. It's called the Ehrhart polynomial. This numerator polynomial is called the H star polynomial. And a really awesome fact about H star is that every coefficient is non-negative. That's due to Richard Stanley. Okay. Now, how does this connect with what we already saw? Well, the sum of these H star coefficients is the normalized volume. So what that means is that this polynomial refines the volume. Take the polynomial, evaluate it at Z equal to 1, you get the normalized volume. So if you expect cool things to happen with normalized volume, you should expect some subtler cool things to happen with H star, right? And everybody likes subtle cool things, right? Like, I think I need a t-shirt that says that. I like subtle cool things. All right.
So for anyone used to Hilbert polynomials
Yeah.
that don't kick in right away because of embedded components at the origin,
Yes.
It's a miracle that this works.
That's right.
Do you understand anything about embedded components? Why?
Yeah, I mean, essentially these are standard graded Cohen-Macaulay algebras.
It's a Cohen-Macaulay.
It's Cohen-Macaulay.
Okay.
Yeah. Yep. So, all right. So let's look at symmetric edge polytopes. So here is the H star vector of a symmetric edge polytope. It's like 1, 66, 1735, 22, 534, 1, 5, 6, 3, 4, 3, blah, blah, blah. And I don't know about you, but I really hate staring at lists of numbers. I just hate it, okay? So I don't do this when I am looking at H star vectors. I always plot, okay? So what I've done here is I've just plotted above 3, I plot the point H3 star, which is 0, 1, 2, 3. 22,534 is this point right here. H4 is 156,353. That's this point. Notice that, I should say the y-axis is on a 10 to the 6th scale, okay? H5 star is whatever it is. I don't know, it's up there. And then you just connect, sequentially connect these with lines. You're just doing a line plot. And so this lets me see the H star vector a little better, all right?
Is there a law of large numbers for huge examples?
Huge is not a well-defined term in this field. And yes and no.
Does that curve converge?
All of those are good questions. Okay, so. All right. That's a different talk. So this right here is, these are 15 random connected graphs, each of which has 15 vertices and 40 edges. Take their symmetric edge polytopes, plot their H star vectors, this is what you get, okay? Now, I claim personally, this is getting to my comment yesterday about distributions, I claim that this is the right picture sometimes, and I also think it's not always the right picture. And the picture that I'm proposing to everyone, if you would like to think about, this is just, you don't have to think with me. Feel free to just think on your own or think with me, whatever. I propose that what we want to do is take this H star polynomial and divide it by the normalized volume. Divide it by the sum of the coefficients. Because what's happening here is you look at this and you're like, well, those all kind of look the same, right? But they're not the same, and clearly they're different. But if you take those 15 and you normalize, what does this do? It makes every coefficient now a non-negative fraction that sums to 1. So this is now a discrete probability distribution. If you plot those same 15, it looks like that. And now I'm like, oh, those are the frickin' same. I mean, they're not the same, but right? They're the same. And so what I would like, so me and Andres and Esme Bajo and Julie Codinotti and Johannes Hofshire have a paper where we've studied asymptotics of H star distributions for a certain family of simplices. Actually, it's local H star, whatever. But I think we should think more about these things, because this kind of thing happens a lot, and it's just cool. So if you want to talk about it, at 4 o'clock today is collaboration time. Just find me, and if you want to talk, we'll just all talk, OK? Yeah.
So just to clarify, if you have a favorite family of polytopes, there's
yes, open problem of your choice. Pick your family of lattice polytopes, plot these, and what I want to know is I don't want to classify the H star vectors, because the H star vectors are impacted by the volumes, and they're all a little different. I want to get rid of the noise of the volume, and I just want to see what the distribution is. I think this is a good direction that we should go, that as far as I know, people haven't thought about. If people have, let me know. Matt, have people thought about this as far as you know? Don't ask you. You wrote the book. Anyway. Okay. So, cool. All right. So that's H star, and I think this is a good thing. I propose we think about it. Don't blame me if it doesn't go anywhere. All right. So another thing that matters in this area is Gorenstein polytopes. These are related to Gorenstein semigroup algebras. There's a whole thing going on there. I'm just going to talk the geometry, okay? So a lattice polytope is called reflexive if the following happens. So first of all, this is up to unimodular equivalence. I don't want to bother defining this. I'm just going to say there's a notion of equivalence for lattice polytopes that preserves lattice point structure. It's the right notion of equivalence for lattice polytopes, okay? So up to unimodular equivalence, you're reflexive if you are a lattice polytope Q, and it has two properties. First, it contains the origin in its interior, and second, its dual is a lattice polytope. Okay? I'll show you a picture in a minute if you're unfamiliar with duality of what this looks like. All right? And your Gorenstein, if some dilate is reflexive, some positive integer dilate. Okay? So, if you are an algebra person, you should think of having Gorenstein of some index, and reflexives are Gorenstein of index 1, basically. Okay? All right. So it's a beautiful theorem that in every dimension, there's only finitely many reflexive polytopes. The number grows incredibly fast. But in dimension 2, there's 16 of them. This picture is from a paper by Punin and Rodriguez-Villegas. And up to equivalence, these are the 16 reflexive polytopes. So for example, in the bottom here, this -1, 1 square, its dual is in the upper right, this little cross polytope, this little diamond. All right? Similarly, if you take this upper left triangle and rotate it clockwise 90 degrees, its dual is the triangle in the lower right, okay? And vice versa. So notice you have to do an equivalence and then take the duals, and then you get all these things. So you get pairs of reflexives. It is possible for these to be self-dual. For example, if you take this hexagon here, if you take its dual, you get this hexagon rotated, again, 90 degrees clockwise, all right? So there are self-dual pairs, but reflexive polytopes come up in mirror symmetry and algebraic geometry and physics and stuff. So in addition to Ehrhart theory and other areas. Okay, so why are these cool for Ehrhart theory? Well, this is a theorem due to Stanley. He proved it in the reflexive case also. Suppose that P has its H star polynomial of degree S. So S has to be no more than the dimension, right? But it doesn't have to be the dimension. It could be smaller, right? Then P is Gorenstein if and only if this polynomial is palindromic, okay? So that means that H0 is HS, H1 is HS minus 1, H2 is HS minus 2. This is a general phenomenon of Gorenstein algebras and their Hilbert series and things like this. But if you're not familiar with that stuff, just start here, all right? It's cool. But one thing that you might have noticed earlier is that for these symmetric edge polytopes, you have this symmetry, right? Left and right symmetry. And that's coming from the fact that a theorem due to Matsui et al. And for connected graphs and Gashitani more generally, that these are reflexive, okay? Every symmetric edge polytope is reflexive, so you'll always see this. So this picture is very noisy. It is 396 random connected graphs with 12 vertices and 30 edges. And I really want to emphasize in all of the experimental data that I'm showing you, you should just take it with a massive grain of salt. This is bad data, all right? And the reason I say that is that there's almost 12.2 billion unlabeled simple connected graphs on 12 vertices with 30 edges per computations by Brendan McKay, and I'm showing you 396 of them. So okay. But already, just with a random sample of 396, you'll notice H5 star ranges from 36,000 to over 70,000. So there's already a big variation there. And what happens when you move to the distributional picture? It's different, but it doesn't look as different, right? And so I just think this is good to study, this is good to study. Okay, that's my sell for thinking about distributions.
What fraction of the reflexive senses comes from these graphs?
I would guess very few, but I don't know because we don't actually know how many reflexives there are in dimensions, 5 and above, I think. I mean, it's 500 million reflexives in dimension 4, I think. So.
Not enough graphs to get anywhere near it.
Yeah, yeah.
Are you using Erdős-Renyi random graphs?
I'll talk about that later. Oh, for this you mean? Yeah. No, for this, I'll tell you also how I got these. Yeah, we use, for these samplings, we're using different random graph models. Erdős-Renyi is one model. There's also a configuration model. There's a bunch of different random graph models. So I'll tell you about that. That's in the second part of the talk. All right, the final kind of background thing is about gamma vectors. This is something you'll hear about a lot from the Earhart people and the algebra people. And so if you start with this polynomial here, 1 plus 11z plus 11z squared plus z cubed, that's the H star polynomial of a 4-dimensional unit cube. It's also an Eulerian polynomial. And what you notice is that since this is palindromic, you really only need to worry about the first 2 coefficients. And we have palindromic polynomials that we all really like, 1 plus z cubed, and 1 plus z, and 1 plus z squared, and 1 plus z to the 4th, and things like that. So what you do is, if you have a palindromic polynomial, you take these binomial powers, and you have to shift them a little. So 1 plus z, I shift by z so that they have the same center of symmetry, right? Z and z squared is the center of symmetry. And then I want to write this polynomial as a linear combination of those, and you see a 1 and an 8 as the coefficient, okay? And this is a general phenomenon. You do this if these coefficients are non-negative, you call the thing gamma non-negative. So generally, if p is a palindromic polynomial, it's gamma non-negative if you have that written as a linear combination of these shifted binomials, that the coefficient, which is traditionally called gamma, are all non-negative. Okay. All right. There's a lovely conjecture. This is coming from the Charney-Davis conjecture, but again, I'm going to try to stay focused. In the special case of reflexive polytopes, this is something called a version of Gall's conjecture. If you have a reflexive lattice polytope, and if it has a regular unimodular flag triangulation that contains the origin in every maximal simplex, the conjecture is that its H star vector is gamma non-negative. This is very hard, I think. I don't know. I mean, Martina's nodding, so I'm not alone. I mean, this is hard. But if you're wondering, like, why do people care about these sorts of things? It's because there are these combinatorial structures for polytopes, lattice polytopes, that seem to yield gamma non-negativity. Okay. So to sum up kind of about lattice polytopes in general, again, if this is just not a field you're as familiar with, maybe you've heard some talks but aren't so familiar, what are the things that people in my world do if they're thinking about lattice polytopes? We want to determine facet or vertex descriptions. That's one thing we want to do. We also want to find interesting or effective volume formulas. These can come in lots of different flavors. Effective might mean different things depending on the context, right? We always want to classify the H star vectors for polytopes in a specified family. That's just like perennially of interest. Finding combinatorial interpretations of H star vectors, again, usually for a specified family is of interest. Inequalities on these H star coefficients like unimodality, log concavity, real rootedness, gamma non-negativity, all those sorts of questions. We want to think about that. Investigating triangulations of these polytopes and the structure of triangulations and the secondary polytopes, stuff like that. And then classifying special families of polytopes like Gorenstein polytopes, polytopes that have the energy decomposition property, smooth polytopes, lattice polytopes whose Earhart polynomial has the canonical line property, blah, blah, blah. There's a long list of these things, okay? If I was only giving a survey talk, then the next half of the talk would be kind of like, what do all these things mean? But instead, I'll just leave this as like a little guide for you. If you're like, I want to know more about this area, look up all these words, okay? Nothing big, an afternoon's worth of work. All right, so let's focus in on symmetric edge polytopes. I have like 3 slides. On the first slide, I'm thinking about kind of what I think of as fundamental results. There's been a bunch of papers on this. I'm not going to talk about every paper, but again, if you're trying to figure out who's done what, look for papers in these years by these authors on the left. And the things I want to highlight is in 2018, Chen, Davis, and Mehta proved that the volume, the normalized volume, always, the volume of an SEP gives an upper bound on the number of solutions to a set of associated algebraic Kuramoto equations. So the Kuramoto equations come from dynamical systems of coupled oscillators where the coupling is controlled by the graph. And so there's interest in applied math in trying to understand how many solutions there are to these systems. And so computing volumes is of interest to them. In 2019, Higashitani, Yuhemko, and Michalik described the facets. I'll talk about that more. They also gave an explicit regular unimodular triangulation using Grosvenor basis techniques. I'm not going to talk about that, but that's in there. As a corollary of these being reflexive and having a regular unimodular triangulation, a result of Bruns and Romer says that these have unimodal H star vectors. So they go up, and then they come down. And we already saw that in all the plots, right? And then in 2024, Martina and company proved that symmetric edge polytopes are unimodularly equivalent to each other, if and only if they have the same, isomorphic graphic matroids. And so this is somehow like a matroidal structure. So if you like matroids, then this is kind of what's going on. And they also extended the definition of symmetric edge polytope to any regular matroid, and that gives what's called a generalized SEP. Okay, so.
I think before you go to the next slide, kind of to give back to Selvi and embarrassing that I just want to make a comment that in 2023, that Kara, Portugal, and Tsuchiya is Selvi, Irem, and Akiyoshi. So in the collaboration time, you should find them.
Absolutely, that's right. That's right. Thank you for pointing that out. I should have done that. All right. Okay. Second, so that's what I think of as some kind of foundational results, fundamental, whatever. So some Earhart theory results. Again, there's been a lot of papers on this stuff, okay, in recent years. So some of the things that we know that I've been thinking about are in 2017, Higashitani, Komura, and Michalik proved that some symmetric edge polytopes have Earhart polynomials with roots on this line, real part of z equals -1/2. That's called the canonical line property. It's of great interest to figure out which reflexive lattice polytopes have this canonical line property. This kind of goes back to work of Bump and Choi and others about what they call local Riemann hypothesis. But these are very interesting objects when this happens, and it's related to Earhart positivity as well. In 2021, Usugi and Tsuchiya, and Akiyoshi, Akiyoshi's here. They proved that, didn't prove anything. They conjectured that symmetric edge polytopes have gamma non-negative H7. What?
No, just embarrassing them.
Oh, yeah, great. Yeah. I mean, it's a nice conjecture. All right. So this gamma non-negativity seems to be a phenomenon here, maybe. It's a nice conjecture. I think we should all try to prove it, and we should all try to find counterexamples. That's what we should always do with every conjecture. Okay. In 2022, Kalman and Tuthmaris have a description of the H star polynomial using shellable simplicial dissections of facets. These are not triangulations necessarily, but they're simplicial dissections. It's pretty interesting. Anyway, that's worth kind of thinking about if you like these sorts of polytopes. In 2023, again, Martina and company proved that gamma 2 is always non-negative, so that's good, and gave some asymptotically, almost surely, gamma non-negativity results. They're a little technical, so I'm not going to go into them, but for Erdős-Rényi graphs. So again, there's some reasons why we might think that this conjecture is true, but except for outliers. Anyway, which is always the problem. By the way, it's really funny. If you talk to scientists and you talk about counterexamples, they don't know what it is. But if you refer to a counterexample as an outlier, they immediately know what you're talking about. Okay. And then in 2024, Davis, Higashitani, and Usugi, they gave examples of generalized symmetric edge polytopes, so the ones that come from regular matroids but not graphs, that are not gamma non-negative. So,
Ben?
Yeah.
Sorry if I missed this and it's obvious, but gamma non-negativity and Earhart positivity, or what's the connection between them?
I don't think they're connected. I have to go back and look. There's a paper by Fulu and Liam Solis that goes through all of these things, and I must admit I always forget.
Okay.
I should
It's
keep
not
it
like
in
if
mind.
you know Earhart positivity, you know gamma positivity.
No. the Earhart positivity, when I think of Earhart positivity, I think more of this canonical line property, because if you have the canonical line property, then you have Earhart positivity, and that's connected to H star because if all the roots of the H star polynomial lie on the unit circle, then you have this canonical line property. So it's different than this real rooted business. It's this unit circle rooted business, so these are Kronecker polynomials. And yeah, so Fu and I wrote a paper about that a few years ago. So, all right. There's also been a bunch of work about facets, and I'm going to talk about that next. So I'm not going to kind of go through the details, but just I'll put these slides on my website soon, and also there's talks on YouTube. It'll be so. If you want to just have a little census of papers. If I missed anybody, I sincerely apologize, and I will fix my slides if you tell me, and I will change on my website. Okay. So part 2, let's talk about some facet stuff. So in 2019, Higashitani, Yohemko, and Michalik gave this description of the facets. So first of all, I'm going to say because symmetric edge polytopes are reflexive, that means that every facet has this form. It's a linear functional with coefficients f, indexed by the vertices of v, less than or equal to 1. Okay, that you can always do that, and the values of f are always integers. That comes from being reflexive, okay, automatically. That's supposed to say a half space. Sorry about that. All right, so what I want to know is which f functions from v to z are facet defining, okay? And the answer is these are facet defining if and only if you have these 2 conditions. First of all, for every edge in the graph, the difference in f across the edge is at most 1 in absolute value. So it can either stay the same, go up by 1, or go down by 1. And second, if you look at the edges that differ by 1 or minus 1, they have to form a spanning connected subgraph of G. So on the one hand, you're like, what a beautiful characterization of the facets. And then you try to work with it, and you're like, it's good we have a characterization of the facets. Okay? I mean, this is complicated. So just as an example, you can use this to show that Kn, I mean the symmetric edge polytope for Kn, has 2 to the n minus 2 facets. So notice for K3 we have 6 facets, which is 8 minus 2. So how do we get that? Well, if you take any non-trivial subset of the vertices and label it with a 0 if it's in A and a 1 if it's not in A, then that gives you one of these, because you're in the complete graph. And you can just check that on your own at some point, or if you get bored later. And that turns out to be the only type of labeling that can arise. I should also say, because these are not full dimensional, these f's, you can shift them by constants, and they give you the same thing. So, okay. Anyway, so 2 to the n minus 2 facets for Kn. So then you can just ask, well, how many facets should I expect to see? Like, give me a graph, I don't know. So this is just 4,874 connected graphs. I sampled them from an Erdős-Rényi, 11 vertices, probability 0.45 on each edge, because 0.5 we always do, that's boring. So like, just play a little, Anyway, have fun with it. Anyway, whatever. But what you can see is that here, the number of facets there, if you look, this is like, 2,175 facets or so. There's almost 700 graphs in this sample that have around 2,175 facets. There's not a whole lot that only have 1,800 facets. There's not a whole lot that have 3,000 facets. So this is this histogram. And for a little context, where does K11 sit? K11 has 2,096 facets. So it's a little on the left. So from this sample, at least, most of the graphs have more facets than Kn. Okay? That's kind of what I'm seeing. And so then you might ask, well, what if instead of just sampling from Erdős-Rényi, what if I sample from some more restricted family? Like earlier, I fixed the number of edges, so let's do that. So how do you sample from graphs on a fixed number of edges? Well, you use Markov chain Monte Carlo sampling. That's kind of the standard way to do this. And what you do is you do what are called single edge swaps. So I start with a graph, and I'm going to assume it's connected. I take an edge at random in the graph, like AB, and I remove it, and I pick an edge in the complement at random, and I put it in. So I take out AB, I put in BG. If I do that and the graph is no longer connected, I just go back and do it again. And I keep doing it, OK? Again, once I get to this graph, I can take the edge AD, remove it, put in a random edge in the complement. That's CD. And so this gives you a random walk on graphs with a fixed number of edges. It has all the lovely properties that you want of a good Markov chain. And when you sample, you don't want to do this once and then sample, right? You want to pick your starting graph, burn this thing a whole lot of times, and then start sampling at intervals, right? Because you want to make sure that you mix it up a lot before you sample. So you're doing this intermittent sampling, OK? So this is around 200 graphs sampled, 13 vertices, 18 edges. And if you look, again, this is a histogram. And so if you have around 9,000 facets, that's where the bulk of them lie around 9,000, somewhere between 7,000 or 8,000 and 12,000 facets, say. And then there's this. So what is that, right? Yeah, so it's an outlier, right? All right, and I will tell you what this is. It's that. And that has 46,656 facets. And I will say that in a way, if you know about reflexive polytopes, I'm not going to go into it, but there's some conjectures, there's some work due to Ben Nil about maximizing facets. This example is not totally surprising if you know about that stuff, OK? But this does beg the question, well, if I just look at all connected graphs on n vertices, what's the biggest number of facets I can get? And what's the smallest? So Katie and I did a bunch of computations, and we have the following conjecture. Do not read the italicized stuff. OK, it's only on there for, I don't know, mathematical honesty or something. OK, so the conjecture, the take-home version is down here. The most facets arise when you have a wedge of triangles like this. Now, there is a problem. If you have a wedge of triangles, you have an odd number of vertices, right? So if you have an even number of vertices, the graph that seems to be the facet maximizer is one of these triangles becomes a K4. So it's either a wedge of triangles or it's a K4 wedged with a bunch of triangles. And that seems to be the maximizers.
So for anyone who does combinatorial enumeration, it's the large automorphism groups that kill you.
Something,
It looks like it correlates.
something like this. It's also something about Del Pezzo surfaces and torque geometry. I don't understand all those connections.
You haven't plotted it against the size of automorphism group.
I have not.
Because that's got a huge automorphism group.
Yeah, it does. And I should, that's a good point. I haven't thought to do that, but I should. But except, what are the minimizers? Okay. Conjecturally, they're complete bipartite graphs where you take roughly equal partitions. So k plus 1, or kk. Yeah, complete graph. If n is 2k, you take complete graph on two shores of the same size, k and k. All right? So, all right, this has been, so Mori and Asugi proves this is true for join graphs, which are graphs whose complement is disconnected. But other than that, this is still very open and seems very interesting. And I should also say, why do we care about facets? One of the reasons we care is because if you're computing the normalized volume, you want to understand the structure of the facets and their triangulations and things like this. So somehow the facets of symmetric edge polytopes play a big role in a lot of the computational things both the applied people and the combinatorialists want to do. So we would like to understand the facet structure so that we can understand, say, triangulations. And H star. Again, that simplicial dissection, that's a dissection of the facets that then get stitched together. So, OK. All right, so, that's one question. What are the biggest and the smallest? Another question you could ask is, what kind of structure in the graph might lead you to have more or less facets? OK? And so one thing that I think all of us combinatorialists should do more is read network science papers. So there's these two groups of people that do things with graphs. And if you are a person who thinks a graph is a graph, then you're not the other group, OK? So essentially, there's all of mathematicians who study graph theory, and then there's everyone else in the universe that studies networks. And there's this huge amount of work in network science, and it's really awesome. And if you've never looked at a book get Newman's book on networks and just like start looking through it. It's full of amazing stuff. It's a lot of people doing physics, and so the proofs aren't always proofs, but it's okay. You can read it anyway, okay? So this is an example coming out of this. So clustering metrics came out of work of Watson-Strogatz on small world networks in the late 90s. So for a vertex V, we're going to let CWS of V. This WS is Watson-Strogatz. The C is clustering. That is the number of edges connecting two neighbors of V divided by the number of possible edges between neighbors of V. So think about it this way. I look at a vertex, and what I want to know is I look at all of its neighbors, and I say those neighbors, they could be connected to each other. Well, if they were connected, I'd have a complete graph on the neighbors, and that has some number of vertices. And what I want to know is what fraction of those, that has a certain number of edges. What I want to know is what fraction of those edges are actually in the graph. That's the local clustering at V. And the average local clustering is the average of the local clustering, okay? So this is a plot. This is every connected graph on 8 vertices. The x-axis is average local clustering. The y-axis is the number of facets. The red line is just a best fit regression, okay? And what you can see is it's kind of messy, but it does trend up. One thing I find particularly interesting is that when your average local clustering is 0, meaning that you're triangle free, right? Then there's like this huge spread of number of facets. I think it'd be really interesting to try to understand this for triangle free graphs in general. It's like a separate world somehow from graphs that contain a triangle. And again, you look at this and you're like, well, okay, but like I'm a mathematician and I have to prove something, and I don't know what to do. So, anyway, tell me you're not thinking that. Come on. Anyway, so what I do is I change the problem, and instead I'm going to look at single edges. So this is now 1,001 graphs with 11 vertices and 25 edges. Again, I'm sampling Markov chain Monte Carlo single edge swap. And now this looks interesting, right? Because I have this clear upward trend, but it's also this like region that you see. And this happens repeatedly, okay, for different samples with different vertices and number of edges. The statisticians call this a heteroscedastic plot because it does trend upward, but as you move to the side, the variance increases. So the statisticians, when I've shown this picture to statisticians, and they're like, oh, it's heteroscedastic, and why is this top thing like a line? That doesn't happen. And I'm like, okay, so that tells me there's probably something to prove, right? But again, this is a tiny sample. There's like lots of these graphs, so I don't know. But you do it over and over, and you're like, okay, maybe at least we can say something about a typical thing.
Sorry, Ben.
Where-
Yeah.
Sorry. You go first. I'm talking a lot.
Sorry, where's your wedge of triangles sitting there?
The wedge of triangles is not here, I think. Is that true? If I have 11 vertices and I have a wedge of triangles, then I've got, I don't think it's the right number of edges. I think that should only have 15 edges. Is that right? No, you're fine. Ask questions.
That's right.
That's good.
Yeah, I guess the question was just, is the line important, or is there like a cone behavior?
I don't know. Yeah, I don't know. By the way, I should say, my purpose of giving this talk is mostly to get you all to work on this. I don't know. I'm going to tell you some theorems, but a lot of this is just like, this is cool. I'm thinking about it, and anybody else can too. It's pretty neat. Also, I just think, I think that we should have a different way of thinking and doing experiments in math than we do, and I think we should be much more willing to give talks that are a little more experimental. I think that's a strength in pure math that we underutilize significantly, and it also cuts us off from conversations with other disciplines. So we act like we're humanists that are always proof-based, but in practice we're very experimental, and we should be very open about both. So anyway, and I'm a full professor, so now I can do whatever I want. And I'm telling you, if somebody's like, well, you can be like, Ben said to do it. Anyway, okay, here's another restriction. So instead of fixing the number of edges, you can go farther. You can fix the degree sequence, which also fixes the number of edges. So this is 192 graphs with 17 vertices and degree sequence 3, 3, 3, a bunch of 4s, 5, 5, 5, 5, and then 15. So it's got a single hub with 15, degree 15, and the rest are all pretty low degree. And now this is very nice looking. And again, many of our plots, especially if you're a little more dense, the sparse graphs tend to be a little worse. If you're a little more dense, then the plots really tighten up when you do the samples. This uses a different kind of Markov chain Monte Carlo sampling called double edge swap. I'm happy to talk about it if you want. And again, it's just on the slides here so that if you're reading it later, you can see what it does. Okay. Again, this is standard Markov chain Monte Carlo sampling for network science people. I will also add that there is a second notion of clustering. You should be careful if you read that literature. There's clustering, there's average local clustering, clustering sometimes called global clustering. In our experiments, it doesn't seem to matter too much which you use, but also all of our graphs are kind of small. So I don't know, maybe one clustering is better than the other, but again, you can see nice pictures. Okay, so let me actually tell you a theorem. Let's think a little more carefully, like how might we go about proving anything? Like what are we looking for? Well, we have these two conditions on what functions give you facets. And what we're going to do is we're going to write G sub f for the facet subgraph, meaning the graph that E sub f is. So you take this spanning connected subgraph of G that supports the differences of 1 or minus 1. And Chen, Davis, and Korchevskaya proved that every facet subgraph is a spanning connected induced bipartite graph. So what you got to do is you got to look at your graph, and you got to look at every partition of the vertices into two parts, look at the induced bipartite graph, check to see if it's spanning and connected, and then find all the f's on that work. So that's one way to do it. OK, that is hard, though. So at first, we just want to have some sense of like, how often do we expect to see one of these graphs, period? Forget the functions. So let B of AG be the induced bipartite graph for the bipartition A and V minus A of G. Okay? And the theorem that Matt and Katie and I proved is if you take an Erdős-Rényi graph, ignore the first two bullets because I'm running low on time. The third one's what really matters for me. If P is 1/2 plus epsilon for epsilon some small value, then with high probability, for every subset of the vertices that has roughly half the vertices in the graph, so the size of A is not too far from n over 2, you have that it's connected and spans V. So it's a facet subgraph. And so what this, and notice, by the way, the central binomial coefficient is really big, right? So this says there's a lot of these things. And every such connected spanning subgraph has at least two facets, because you can put 0 on one and 1 on the other, and there's two facets. So yeah, so there's a lot of these things probabilistically. But again, if you start looking at specific examples, it's kind of like, huh? So let me show you a specific example, and we're going to end with a conjecture about these things. So these are generalized theta graphs. What you do is you take a vertex at the bottom and a vertex at the top, and you connect them with t paths. And the lengths of those paths are going to be m1, m2, down to mt, weakly decreasing. Okay? And so you could ask, like, OK, if I have a graph like this, please tell me I can count how many facets there are. And you can. So Katie and I proved that if all the, we have a general result, but for the talk, I'm just going to focus on the case where all the path lengths have the same parity. So these are either all even or all odd length. Then the number of facets is given by this function. It's a sum from 0 to mt of mt choose j times this product of other binomials. OK. What does this actually look like? And this leads us to our conjecture, OK? So ignore everything on the slide for the moment except this top line. So let's just suppose that I have 3 of these, not t of them, OK? Then what is this product of binomials? Well, you take the x3th row. Oh, sorry, I'm going to switch from m's to x's. My apologies. So x3 is the smallest, x2 is the next smallest, and x1 is the next. Sorry, x3 is less or equal to x2 is less or equal to x1. So you take the x3th row, the x2th row, and the x1th row. And so those are going to be 3 rows in the middle of this picture. And for each entry in the shortest row, you take the 3 values in that column from those 3 rows, and you multiply them together and add them up. So this is 1 times 6 times 28 plus 4 times 15 times 56 plus 6 times 20 times 70 plus, et cetera. That's what this function is doing. And the conjecture that I'll leave you with, we don't know how to prove it. We worked real hard on this. I've showed this to some analytic number theorists. I've shown it to some combinatorialists. It's cool. The conjecture is that if you take 2 edges away from either the right or middle path and instead insert them for the left path, so you take edges away from the shorter ones and put them into the larger ones, the conjecture is the number of facets grows. So what this means for binomial coefficients is that if I take these 3 rows and I move the top row down 2 and the bottom row, sorry, the top 2, let me start that again. If I take these 3 rows, I take the top row up 2 and the bottom row down 2, and I do the same game, I have slightly fewer terms that I'm adding because I've dropped by length 1 on each side, but the values are bigger down here at the bottom. And again, my suspicion is this has something to do with the central binomials, but I'm just having trouble figuring out how to make that happen. But I think this is just an interesting combinatorial question, period. Take these things, take these triple products, add them up, move the rows up, and this middle row you might not be able to move up if they're too close. But if they're kind of spread far apart, you can move the middle row up and the bottom row down also. The same thing happens. We've checked this up through all partitions of n with 3 parts with n equal to 400. So, I mean, we think it's true. Anyway, but I don't know. I would love for somebody to figure out why this works. And it just gives you this sense that, like, OK, the structure of the graph should say something about facet numbers, and there's things to be done here. So I will stop there. Thank you very much.